agenda items, okay? And so again, you should find that, okay? So today, if you're having to watch this from home, it's 3:13, and we're talking about power. Power is very much related to work, and in this case, it's the rate at which we do work. Or, very generally, we could say it's the rate at which energy is transferred. So sometimes it's just a work mechanism, other times it's energy transfer. And so since work and energy are very similar, we can say it's the rate at which we do that. How many people have to walk up the stairs like numerous times during the day? Of course. When you walk up the stairs, you are doing work against gravity. Whether or not you walk or run, the same amount of work. So you're doing work against the gravitational force. It's the same amount, whether or not you walk or run. What happens when you run? Does your heart race a little bit? So your engine for your body is your heart. The engine for your car makes you speed up more quickly. If you want to run up the stairs, you're going to have to do work at a higher rate. That means your heart's going to have to beat faster. When you run up the stairs, more power is being developed because you're doing that work more quickly. Again, just as an analogy, your car engine revs, the greater that horsepower is, or the greater the rate at which you're doing work. Your heart does that revving when you do work more quickly. Athletes often will measure their power output doing a variety of activities. As a matter of fact, some of you guys watch like the combine stuff for the NFL. Raise your hand if you know what I'm talking about. They're always talking about, let's run the 40-yard dash and all these kinds of things. They're looking at what these athletes can do. Most of these things that the athletes are doing are power-related activities. How quickly can they get something done? And so power. Now, let's talk about that from an equation standpoint. Power is just work over time. It's a rate. We can also think of it as just, in general, we can say energy transferred. I'm going to abbreviate that as XFER. Just transfers, abbreviation for that. So energy transfer divided by the amount of time. Now, we often write letter equations. And so I want to take a moment and show you what those would look like on your equation sheet. The bar over top of the P represents average power. Now, we got to be careful here because we used the symbol P before to represent momentum. You guys recall that, right? So oftentimes you're going to see same letters representing different things. You have to use the context of the problem to understand which one is which. So power I could write as W over T. And there's one more way that I could write that. I'm going to take that work and I'm going to split it up into two different things, force and distance. So let's go ahead and write that as force times distance divided by time. And then through the power of, like the magic of mathematics, I'm going to take the distance and group it with the time. And I'm going to do that with some color coding. We're allowed to do that math. It's called the associative property. So instead of grouping distance with force, I'm going to group distance with time. Some of you might recognize that distance over time represents a speed. And so I can think of that as power is equal to force times velocity. Now, I want you to think about one of the combine activities. Yeah. One of the combine activities is like an athlete might do something like this. We're like, all right, you're going to have to, are you ready? Oh, you got to put, were you trying to mess with me? Get your feet off the ground. All right, so I have to do some work here, and I'm going to push them up. Are you okay? Okay. Like how much force am I exerting and how quickly am I moving? I can just multiply those two numbers together and I would get my power output, okay? So it's that idea. How quickly am I doing that work? Okay, there we go. Would you guys agree I expended a lot of energy in there? And the rate at which I expended that energy is what we call power, okay? That idea. Thank you. Was that sort of fun? Yeah. Well, thank you. All right, good. Always like to have fun in class. All right. Now, let's talk about units. 1 watt. I think it was Brody. Is this correct, Brody? That you shared the watt as a unit before. The watt is the unit of power. 1 watt is equal to 1 joule of energy, of work done or energy transferred in 1 second. Now, I know that there are people in here, they don't always volunteer for this kind of stuff, but I know there are people in here that are car people that like working on engines. I would not use the watt to talk about engine power. What would I use? I use horsepower. So the horsepower is originally defined based on horses doing work plowing fields. You might appreciate this, Kayla, because you said dairy farm. You also do horses or cows, or is it just?
It's just cows.
Just cows, okay. But horses are really cool animals, right? Originally, agricultural society were like, hey, we got to plow these fields. And they're not doing that with shovels, right? In the beginning, they said, well, let's just have horses do this work, right? So they hook on the harness and they have the horses plow the fields. They say, well, what's the rate, average rate at which horse does work? We call that horsepower. Not very scientific, right? Okay. 1 horsepower is 746 watts. That's the conversion. So when you're talking about engines and things like that, you'll probably go to the horsepower. All right, a carryover from your 8th grade class. When you guys were, if you're a senior right now, this is like 4 years ago. If you're a junior, this is like 3 years ago. You may have seen this picture before. You don't remember it. But Jim and Michael are both doing how much work? When you look at that diagram, how much work do they do? The barbell is 100 newtons in weight, and they lift those things 2 meters, so they do 200 joules. So each person does 200 joules. Just 4 stem systems. However, you notice that Michael takes him only 1 second to do that, whereas Jim is taking him 10 seconds. So even though they do the same amount of work, they develop different amounts of power. So power that Michael develops is the work that he does over the time, 200 joules in 1 second, means that he's doing 200 watts. He's developing 200 watts of power. Would you please raise your hand if you've ever been on an exercise bike of some sort, and you're pedaling along and it tells you a power output, and you can see the faster you pedal, the more power. You've seen that? A few people? Okay. That's the idea. Power is a rate. Now, Jim does the exact same amount of work, but he does that in 10 seconds. So the rate at which he's doing work is 20 watts. Same amount of power, or same amount of energy, same amount of work, but different rates. Okay? All right, that's a new equation for us. If you can do work, you can do power. You just have to deal with the time element. I like to do this demonstration with light bulbs, just because, well, most people, when they think of wattage, they think of light bulbs. I'm going to have you just come around up here for a few minutes. Just out of your seats, just come on up. You okay?
Yeah, I'm just really tired.
Oh my gosh, okay.
Whenever I yawn, my eyes water.
I wondered if you needed to take a break for a second. Like, oh,
No, whenever I yawn, my
it's all
eyes
good.
water.
It's all good. It's all good. I was just like, oh man, that's feeling. So I didn't want to embarrass you.
All the time. All my teachers say, "Sir, you okay?"
It's all good. It's all good. I was just like, just for a moment. I'm like,
Asking every other day, like, "Are you good?" So I have tears becoming.
Yeah.
It's okay. Oh, you're not taking that.
Yeah,
It's
I,
not as nice as that.
I don't want to take
Oh yeah, right in the very front class.
Oh, yeah, did this happen maybe before and you were back and never even noticed or something?
Yeah, it happens all the time.
All right. So anyway, so go ahead and draw unnecessary attention. All right, so guys, here we go. I only do this, wait for it. I only do this demonstration with my brightest classes. Thank you. Nothing, I mean, it's bright. You guys are bright. All right, thank you. I know, I'll be here. I might not be here all week next week. You guys know, did I share that with you guys? What? I thought I shared this. I got selected for jury duty, right? So I did share that. It's next week and the week after. I might be gone for, okay, I got to go and report to a courtroom for, it's 2 weeks starting next week. So if I'm out, You guys just gonna be on your own. Can you guys handle it? No, there'd be a sub, but my gosh, I'd be like, how do I do this? I gotta have a prepare for you guys, got to prepare for AP Physics and, just crazy. I hope I'm not going, but in the event that I am, you guys be good to that stuff. All right. Now, this is an incandescent light bulb, and Seppi can look closely at that and tell me the power rating on it.
60 watts.
60 watts. So as I plug this thing in, the rate at which energy is being transferred from electrical into light is 60 joules per second. This thing's been on for 10 seconds. How much energy was used? 600 joules, right? It's on for 20 seconds. 1,200 joules. It's using energy at a certain rate. Now, that's a 60-watt light bulb.
75.
75. What do you think? How's it going to compare? In terms of bright, would you guys agree it's going to be brighter? Can you guys tell that that's brighter?
Yeah.
It's a little bit brighter. Not that much. I actually brought out a sensor in my first hour, and I actually measured the intensity on it, and I showed that. It just takes a long time to get that set up, and they ran out of time to complete their homework, so I'm not going to do that demonstration with you guys. I had this thing set up here. That's reading about 33% of full scale. The other one was about 25% of full scale. And so it gives off more light. Now that was a 60 watt and a 75. Ow, that was really close. Jack, it's a good thing. It's a good thing I exercised a little bit prior to that so I could be that quick. You guys notice that? Like lightning quick. Are you guys ready? 60, 75. Estimate for me, Seppi. I don't want you to look at this. Don't look at the power rating. Look at the brightness of it. Don't look at it. Don't look at the stamps that are on there. Don't look at that.
All right.
Now he's looking. Is he looking?
No.
All right. Don't look at it. It takes a moment for this thing to heat up, if you will. You guys notice the bottom portions are really bright. Top portions are getting brighter.
Oh yeah.
Just like you guys. As you are in this class longer and longer and longer, you get brighter and brighter and brighter. You really do. So just like you guys, this light bulb is getting brighter.
Yeah.
Based on the brightness that you saw from this was the 60, this 75 watt. I plug that. Ooh. Okay, those of you that are close on this side, can you guys tell me the difference in brightness there? I know I only have one of these outlets here. What difference in brightness? This one? It's hot. Be careful. Plug it in.
I can't see.
You like?
Oh my gosh. All right, can you guys see it better? How do their brightnesses compare? This one's brighter? How much power does this thing develop? You say that was 75. This one is how much do you think?
I got like 100.
Yeah, pull that thing out. It's hot. Wait for it. Okay, look and find the power rating. Look and find the power rating.
This.
Wait. Don't say it.
All right.
Wait. Imagine this is a microphone.
Really?
All right.
Say it. What's power rating?
23 watt.
Low mic drop, right?
Yeah.
It's only 23 watts of power and it's brighter. How the heck does that happen? It's more efficient, right? It's more efficient. That light bulb is a lot more efficient in converting electrical energy into light than this. Now this was hot, correct? You felt it? What? I feel that it's still warm. I feel it. It's still warm. Most of the energy that goes into this thing to convert into light is actually converted into heat. This is a very inefficient light bulb. About 3% efficient. What that means is out of the 60 watts of power that this thing's drawing, what's 60 times 3? 180? divide it. It's only about 160 times 3, is that right, 180?
Yeah.
Okay, but as a percentage, that'd be 1.8 watts is going into light. The other 58.2 is going into heat. This is really good for your Easy Bake Oven. Raise your hand. You've actually cooked with this on an Easy Bake Oven. Come on, I want to know who you are. Really? Easy Bake Ovens? Jack, you had to have done this.
I don't know if I don't know.
I still do this, right?
My
Because
neighbor has one.
thank you. This is really good for Easy Bake Ovens. Not so good for heating your house. This was 23 watts of power, and this is 60 watts. This is 23. It uses 3 times less energy than that with the same amount of light output. This was the original version of the LED light bulb. You guys know what LED stands for? Light emitting diodes. Those things are highly efficient. Now,
It's not that bright.
it's not. What's its power rating?
This is wasn't it like 15 watts.
I think it's like 13 or something like that. I mean, something really. The idea here is that they just don't use energy at a really high rate, which means that we can light our homes, we can do all this stuff with less energy, and that's the big idea, right? So it's about efficiency. Anyway, I hope you guys enjoyed that a little bit. It's fun for you guys to get out of your seats, for me to get you guys out of your seats for a little bit, at least. But now we need to head back. Okay, to our seats. So I know. Jack, I'm not going to push you back. You just walk.
Can you tell us a few more jokes?
I'm all up. That's pretty good.
Yeah.
Let's see. I got to think of. I'll think of one before you guys. On the spot in the.
All right.
Okay. This pig going to a restaurant. It's one of those restaurants that's like a black tie establishment. Right? It's like really fancy. Raise your hand. You ever been to one of these things? Okay. Fancy restaurant. Goes up. Maitre d' stops and says, "Oh, wait a second, pig. You can't come in here. You gotta wear a tie." He said, "I don't have a tie. I'm just a pig." So he sends him away. Next day, he goes back to the restaurant. Says, thinking that a different maitre d' will be there, and tries to let him in. And he goes, "Oh, pig, you can't come in here. You gotta have a tie." Comes back a third day. This time, the pig gets smart. In his trunk of his car, I don't always drive a car, but in the trunk of his car, he pulls out. He looks in there, scrambles around, trying to find a tie of some sort. Can't find anything, so he finds jumper cables. That's all he has. So he takes jumper cables, takes them, ties them around his neck in the shape of a tie. Goes up there, he stops, says, "Pig, you can't come in here. You got to wear a tie." He goes, "Look, I'm a pig. I don't own a tie. All I have is this jumper cable on here. Looks like a tie. Let me in." He goes, "All right, pig, you come in. Just don't start anything." Did you get it?
Yeah.
Really? That's like a really good joke. All right. All bulbs convert electrical energy in other forms. Power measures the rate of that reaction. All right, that was that conversion. All right, don't make me cry now. What's different about these things is their efficiency. Okay, so and their life, and their life efficiency or life expectancy. So these light bulbs down here are about 3% efficient. Crazy. You guys are like, oh, but you're gonna be telling that joke tonight around the dinner table. I know you are.
I best believe I'm not.
You say it again. What's that?
I best believe I'm not telling that joke.
You should tell it. Yeah, your family members will find that super funny. All right, these are about 20% efficient, and the LEDs are in the neighborhood of 60 to 70% efficient. And so again, the idea there is that we just get much more bang for our buck. And so a lot of this stuff for this unit is understanding ideas of efficiency. Now we have to do a couple of problems. So I'm going to give you guys just a few examples here. That would allow you to apply these equations. It's not super fun, but it is an essential part of this particular portion of class. This picture is from a Rocky film. Which of the 20 Rocky films that were created is this one? Raise your hand. You've seen Rocky films before. All right, this is one of the favorites. And it came out in the 80s. Yeah, thank you, Jake. Thank you. No. Yeah, it's the fourth one. In the third one, he fights Mr. T was his name, but in the film it is Clubber Lang. Really good, really good movie. It's probably my favorite of the ones. This one came out. I was a junior in high school. This movie came out. It's Rocky IV, and in this one he fights Ivan Drago, and he has to go over to. At this point, it's called the Soviet Union. Soviet Union has collapsed, all that kind of stuff. But back in the 80s, it was all like, oh my gosh, we got. So anyway, Rocky is pulling along his brother-in-law. Quick little name. What's his brother-in-law's name? Paulie, right? So Paulie is sitting there on that sled, and Rocky's doing some work. Sort of like me, I was trying to relive the Rocky days with pushing Jack around here, but. Rocky pulls a 1,200 Newton sled along a snowy path by pulling horizontally along a rope. Rocky pulls with a force of 500 newtons. The sled moves 3 meters in 5 seconds. How much work does Rocky do? How much power does he produce? So my question for you is this. Which force value do I use? The 1,200 Newton? The 500 Newton? Do I add them? Do I average them? Do I subtract them? What number do I use for this? Because we can all multiply numbers, but we have to know what numbers to do. Take a moment and tell that person that you're sitting next to which number we use. The 1,200, the 500, add them, subtract them, average them, which we use. Oh my gosh, I forgot that joke. I'm recording that.
Yeah.
A what? What much? That's the right way to say it, isn't it?
What much work?
You're saying this is wrong? Oh gosh. Okay, so you're saying how much? Okay, thank you. You know what? You don't until you read it out loud. You even know what it says. Okay, thank you. How much work? How about it? Which one do we use? 1,200, 500, the addition, the sum, the average. What do we use? Thank you, Ian. You would think so, right? You would think so. Thank you for trying. Seriously, I appreciate it. Not many people are willing to answer those things. I do appreciate you trying that. Would you agree that this is the weight of the sled? 1,200 newtons. Is there another force that acts on that besides the 1,200 newtons of force? That's the ground pushing them up. Do either of those act in the direction of motion? No. Even though those forces are present, they're not doing work because they don't lie in the direction of motion. So there's a tension force here, and that tension force is the 500 newtons that Rocky is exerting on that sled. Now, probably there's some frictional forces because he doesn't move that sled, just like when I was pushing Jack around, I was pushing him at a constant speed. There's probably something that he's having to do work against. Which one do I use? I use the 500 newtons because that's the force that he's exerting to do that work. So I wouldn't add them, and I appreciate you trying. Yeah, right? I appreciate it. But, when we give these kinds of questions, when I give those, oftentimes in the real world, you're like, why don't you just give me what I need to know to answer the question? Real world, no one gives you anything. They say, solve this problem. And you have to figure out what you need to know to be able to solve it. So this is sort of a step in that direction. You have to evaluate what information is given to you and what is actually important. So for this particular one, I would say work is force times distance. And that force that I exert is the 500 newtons, because that's the force he's doing work with. Moves at 3 meters. Multiply those together, I get 1,500 joules. And that's the work he does. Now, if I'm interested in the rate at which he's doing that, well, that's just a work over time. So power is W over T. 1,500 joules. He does that in 5 seconds. So the rate at which he's doing work is 300. And then we say 300 watts. Raise your hand if you've ever done any chin-ups. Good. When you do chin-ups, you're doing both positive and negative work at times, right? So let's just take a moment. Imagine this is a chin-up bar, and I'm doing some chin-ups, and I'm lowering myself and doing those chin-ups. When you lift yourself up, what kind of work are you doing? Positive. When you lower yourself, negative. Guy weighs 750 newtons, does chin-ups. He's doing 8 of those in 30 seconds. I want to know how much work he does against gravity. That'd be the positive work. Can you guys do that one on the left? He weighs 750, 50 centimeters in length for his arms. He's doing 8 of those. How much work does he do against gravity?
Wait, what do you multiply it by? Times what? Times 5? 12.5.
Is it okay if I just do 8 of those?
375.
Like I don't have to do 8 individually. I can just do a product, right? 8 times 750 times. What should I use for the length? You guys okay with what I'm doing there?
Yeah.
8 times. He's doing 750 newtons of force. That's his weight. He's doing that through half a meter. Multiply those together. I think if memory serves there, I think that's 3,000. I think 8 times 750 times 0.5. It is 3,000. Okay, so in that process, he's doing 3,000 joules of work against gravity. Now I want to calculate his power output. I'm going to take a little bit of a stretch here, and I'm going to say that the power he develops, I'm going to say that that's related to the absolute value of the work that he's doing, because even though he's doing 3,000 joules of work positive against gravity, would you agree that he's doing negative 3,000 joules of work as he lowers himself down? And can you get strong both doing positive and negative work? So even though the left-hand side was just saying how much work does he do against gravity, the right-hand side is talking about how much power is he developing. I'm going to take the absolute value of that. So 3,000 when he's lifting himself, negative 3,000 as he lowers himself. I'm going to say that the total work he does, absolute value, is 6,000 joules. And that takes him 30 seconds. So the rate at which he's doing work there is about 200 watts. The rate at which he's doing work. Okay? All right, last question. My car, 2,100 kilograms. That would be cool to have a car like that. Looks pretty nice. The total of all opposing forces acting on the car while driving along the highway speed is about 29 meters per second, about 450 newtons. How much power must the car's engine develop to continue moving at that speed? What I'm going to ask you to do is I want you to draw for me a force diagram on that car moving along at a constant speed along the highway. See if you can put in appropriate values for forces, arrows, all those things. See how well you do on that. That car is moving along towards the right, 29 meters per second. What would the force diagram look like for that car? Okay, give it a go. Once you have it, I want you to share with that person that you're sitting next to. See if you are in agreement with that double partner of yours. If you know any values, label them with a number. If you know values, label them. If you don't know values, leave them blank. But right now, do the best that you can, then share.
Yeah, like with your arrows and stuff.
Liam, how you doing? I know you came in a little bit late, but you were expert or whatever. I said you were the attendance, so you were school related.
Yeah. Wait, we'll see. 2,100.
All right, here's the FBD force diagram. Should look something like this. You should have a downward force. What would you label that as a number? 2,100 kilograms would be the mass, but I would like to know its weight. So in that case, it would be 21,000. And that again is because mass and weight are different. Mass may be 2,100 kilograms, but if I multiply that by G, and G is about 10, then that weight is about 21,000. Now, there's an upward force, and I'm sure that you guys recognize that upward force would also be 21,000. And that's because the ground is having to push upward to keep that car in a state of equilibrium that way. Okay? The car is moving to the left. Neither of those forces do work. No transfer of energy done with those forces. The total force of all things like air drag and stuff like that is 450 newtons. That way. Take your foot off the gas, the car immediately starts to slow. The reason for that is there's resistive forces there. You might call that the force of air resistance or drag forces. The question I have is, what's that forward force? Where does it come from? Where does it come from? So the engine burns gas, goes through the pistons, pushing up and down on the cylinders and stuff like that. That turns the crankshaft that gets the wheels to spin, and then the wheels push on the ground pushes on the car. How big is that forward force? Turn and tell that person that you're sitting next to. Same size, bigger, or smaller than that 450? Same size, bigger, or smaller?
It will. Because you gotta have like the equal and opposite reaction.
Newton's first law says an object in motion will stay in straight line motion unless acted on by an unbalanced force. If that car is moving, it only needs to continue moving by exerting 450 newtons, right? So that forward force that comes from the engine pushing on that car is exactly the same size as the other, 450 newtons. We don't need force for motion. What do we need it for? To change motion. And so that car's moving just exerts a force of 450 newtons. Now, I only have a couple minutes. I'm not going to give you guys an assignment today. We have one for tomorrow. But let's finish this one up. If I want to use power as work over time, I would rather write that as force times velocity. Because in this case, I know how fast that object is moving. I'm going to use the force times velocity there. It's 450 newtons is how much force that engine has to be able to produce. And I'm moving that at 29 meters per second. And so if I go through and just multiply those numbers together, what I get is about 13,050 watts. Now, for those of you that are more interested in engine stuff, I'm going to take that and convert that 13,050 into horsepower. And that's only about 17.5 horsepower. For those of you that are engine people, you know that that's not a high horsepower. I don't need power to move along the highway at constant speed. Where I need that power is for accelerating. If I want to get to 0 to 60 really quickly, I got to do that work quickly. If I want to tow something, that backward force is not going to be 450 newtons. It's going to be a lot greater. Folks, is it okay if I don't give you an assignment to take home with you? Sorry about that. It could have been my joke that took us out of the but anyway, since you asked.
Yeah.
You can tell that. You can tell that joke. You can tell that joke tonight. All right, guys, have a fantastic day. We'll see you tomorrow, and we will do some power-related activities tomorrow. What were you going to say?
For the last one. Oh.
You were saying what?
You should do a daily joke from now on.
How about you start